You will recall from chapter 5 that energy cannot, I am just reading. All right, let's get going here. Okay, so we're getting into chapter 19, which is looking at energy and thermochemistry, thermodynamics, when it pertains to chemistry. So the first law of thermodynamics is the idea that energy can't be created or destroyed. So that means that the total energy of the universe is constant. So we don't get new energy, it just changes. Energy can, however, be converted from one form to another or transferred from a system to the surroundings or vice versa. There are certain ways that a system is going to move. So typically we refer to it as the spontaneous process, or kind of what's going to happen if nothing influences it or nothing kind of intervenes. So a spontaneous process are those that can proceed without any outside intervention. So here we have two chambers. One is filled with gas at 1 atmosphere pressure, and then the other one has nothing in it. Well, if we're to release the valve in the middle, you would expect the gas in B, side B, to spread out into side A so that the pressure becomes equal, and you get basically, because the volumes are doubling, you get half of pressure. And so it's going to move spontaneously to the lower one. It's not like you would have the lower one and suddenly all of the gas would pack itself into side B and leave the left side unevacuated. So you can kind of think of that example when thinking of this version between spontaneous and non-spontaneous. And that is what I just described. So you can read through that if you want. So another idea to think about spontaneity or spontaneous processes. So we have this nail, it's outdoors, okay? If it sits there, over time, it's going to rust. It's going to develop iron oxide on the outside. So that is the spontaneous direction that it would go. You would not expect a rusty nail to suddenly spontaneously become non-rusty, okay? So that would be the non-spontaneous direction. Processes that are spontaneous in one direction are non-spontaneous in the reverse direction. Processes that are spontaneous at one temperature can be non-spontaneous at other temperatures. So example being, at temperatures less than 0 degrees Celsius, water becoming a solid is the spontaneous direction. But at a temperature greater than 0 degrees Celsius, then the spontaneous direction for water is to be a liquid. So obviously at different temperatures, different directions are the behavior. And I just said all that stuff. All right, what about a reversible process? So in a reversible process, the system changes in such a way that the system and surroundings can be put back in their original state by exactly reversing the process. So this would be the idea of systems and surroundings relationship. So let's say you have a change in temperature, heat goes out of the system into the surroundings. To reverse it, we simply have the heat go from the surroundings into the system, and it's going to go back. Okay, now think of an irreversible process. An irreversible process cannot be undone by exactly reversing the change to the system. So here we have a movable partition. Okay, we've got a gas, we've got a vacuum, we have a piston. Okay, if I push that piston, so spontaneous processes are irreversible. So, oh, sorry, let me go back to that little image. Okay, so if I remove that partition, the gas is going to move and fill the whole chamber. Okay, that's the spontaneous thing that's going to occur. But if I push the piston, okay, it's going to obviously force all the gas back to that side. But I've now done work on the system, and it's no longer spontaneous. So because I've had to add it to it, so it's not reversible. All right, entropy. Entropy is a term, okay, coined by Rudolf Clausius in the 19th century. But this is a concept that is related to to spontaneity. So basically, this guy was convinced of the significance of the ratio of heat delivered and the temperature at which it is delivered. So Q being heat and the temperature at which that heat is delivered. So we can think of entropy as a measure of the randomness of a system. So how much disorder or randomness exists around the particles. And it's related to various modes of motion in molecules. So if you think of like solid water versus liquid water versus gaseous water, okay, they have different levels of randomness. Solid water is going to have the most order, right, because all of the water molecules are in solid form. They have hydrogen bonding to each other, when you have water molecules in the gas phase, very random. They're moving around, very little interaction between the individual particles. So like total energy, E, and enthalpy, H, entropy is a state function, okay? So, so delta S, so the change in entropy is equal to the final entropy minus the initial entropy. So the change in disorder or randomness is related to the starting randomness versus the ending randomness. For a process occurring at constant temperature, an isothermal process, the change in entropy is equal to the heat that would be transferred if the process were reversible divided by the temperature. And I know this is all at times a little bit overwhelming, but the use of or going over practice problems is always going to be the easiest way to kind of explore this stuff. So the idea or the second law of thermodynamics is related to this idea of randomness. So the second law of thermodynamics states that the entropy of the universe increases for spontaneous processes, and the entropy of the universe does not change for reversible processes. Now, what that means is that everything is moving towards greater randomness if inputs are not included. So, in other words, for reversible processes, the delta S of the universe is equal to the change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings, and the total should be equal to 0. For irreversible processes, things that are spontaneous, the change in S of the universe is greater than 0. It will increase the randomness of the system because it's the spontaneous direction for it to go. So these last truths mean that as a result of all spontaneous processes, the entropy of the universe increases. The universe is becoming ever more random. We're going to stop at that point. We will get deeper into entropy when we're talking about at the molecular level, what does it mean? But we'll just leave it at that, and I will see you in class.